Once this is returned, know that n-1 elements of the array are sorted. The only thing that remains us to do is how to insert the nth element into its correct position. And this we do by first by comparing the last element with the element at n-1, and if the nth element is smaller, we just shift the n-first element to the right by 1, and we keep on doing this until we find some element in the array that is already larger than the nth element, and at that position we insert the nth element. Okay, and we analyzed the running time of this insertion sort algorithm. We basically did two types of runtime analysis. One of them was the worst case, right, of this algorithm. We could do it that way as well. Let's do it. This time let's try to analyze this running time by working with recurrence relations. So remember that recurrence relations are basically functions, recursive functions, that we can use to describe the running time of a certain algorithm. So we denote the running time of the algorithm with Tn. This is the function that denotes the running time. If we want to define this Tn, since the algorithm insertion sort is recursive by nature because it makes a recursive call, we can write down, we can describe its running time using recursion as well, or in other words, using a recurrence relation. Let's try to do our worst case analysis by writing a recurrence relation. So Tn is equal to. Note that in this part of the code, we only spend constant time. We'll get back to that later. In this part, we make a recursive call to our insertion sort algorithm with an instance of size n-1. So we down time this recursive call. Since Tn indicates the running time spent by insertion sort for n items, the running time spent for the insertion sort call on n-1 items will simply be T of n-1. Okay, so this is the running time spent for this recursive call, plus the times that we spent in the rest of the code. Remember, this part was simply constant. This is simply constant. How much time do we spend in the while loop? Now that depends on the array that we are trying to sort. In the worst case, it will be the case that the nth item that we want to insert into our sorted array will be the smallest element among all the n-1 items of the array. In that case, this while loop will keep on repeating n-1 times, or almost n times. So we can simply say that this while loop requires some constant times n time, because in the worst case the while loop will repeat almost n times, and inside the while loop and for the comparisons we spend some constant amount of time. Note that this c times n time that we consider already covers the running time spent in the rest of the code. For instance, this part is simply constant, this is the constant, simply. So c times n covers the while loop, the time spent in the while loop, and also the time spent in the rest of the code where constant running time is spent. So T of n-1 for the recursive call, and C, some constant C, times n running time for the rest of the code. Is this discussion clear so far? Is the discussion clear so far? Okay, so we noted that this recurrence relation, or this recursive function, this describes the running time of our insertion sort algorithm for the worst case. Okay. Now note that just by looking at this function, it's not easy to see whether this function is a large function, or in other words, if the running time is large or not. So we usually don't leave the recurrence relation in this form where it is defined recursively, but rather we try to find an open form formula for this T of n. Remember that open form formula is basically anything that is not any function that is not described, that is not defined recursively. So for instance, Tn equals n log n is in open form. Tn equals n cube is in open form. Because with such functions in open form, we can tell whether the running time is good or it's not good. So if we want to write down such a recurrence relation in open form, we can actually expand these recursive parts. So for instance, if we were to expand T of n minus 1 using the definition of T of n, we will simply replace n with n minus 1 in the whole formula. So T of n minus 1 would be T of n minus 2, T of n minus 2 plus some constant times n minus 1, c times n minus 1. So note that the term in here, T of n minus 2 plus some constant times n minus 1, describes as T of n minus 1. So plus the previous c times n would give us, again, the whole sum should give us T of n. In the next step, we could expand T of n minus 2, and then next we could expand T of n minus 3 all the way down to T of 1, which would be a constant. And what would remain is to sum up all the terms. So we have Cn in here, C times n minus 1 here. Next step we would be n minus 2, C times n minus 3, and so on. So the whole sum would be some constant C times 1 plus 2 plus all the way up to n. So that summation is something in the form n squared. 1 plus 2 plus all the way up to n. Because the formula for that is n times n plus 1 divided by 2. So if we keep on these expansions, if we keep on doing these expansions, at the end we will see that this recurrence will evaluate to something of the form some constant a times n squared plus some constant b times n plus some constant c, which we will say that this is equal to theta of n squared. Okay, we will later on see a formal definition for theta to see that this function a n squared plus b n plus c actually is theta of n squared. Okay, so in the worst case, we conclude that in the worst case, insertion sort requires theta n squared running time. If we were to do the best case analysis, how would we write down this recurrence relation? So this is for the worst case, this whole analysis. If we were to repeat the analysis for the best case, how could I write down the recurrence relation? Any ideas? So, Metehan, for instance, do you have any idea? So does everybody understand what the question is? We want to describe the running time T of n of the insertion sort algorithm. We want to define it recursively for the best case, just as we did in here for the worst case. For the worst case, we said T of n is equal to T of n minus 1 plus some constant times n. How can we do the same thing for the best case, for the best scenario? Any ideas? No ideas? So can you all still hear me, by the way? Is there any problem with the connection? So Faizenur has some idea. So for the base case, uh, just this part will run, but we are not asking about the running time for the base case, Faizenur. We are rather asking for the best case. So this is the worst case. This analysis in here, I cannot very easily type with this thing. This is for the worst case. This analysis in here. How could I do the same thing for the best case? Best case analysis. How could I write Tn in this case? Yes, that's a good starting point, Beril. So for the best case, let's try to write down T of n as a recursive formula for the best case. Again, we would spend constant time in here. And again, we would spend T of n minus 1 for this recursive call. T of n minus 1 for the recursive call. Why would we spend this? Because we assume that Tn represents the running time of insertion sort of n items. Then this call in here should take T of n minus 1. Because this call is again on insertion sort, but this time on n minus 1 items. Plus the time that we spend for the rest of the code. What is the time that we spend for the rest of the code? Constant time in here, constant time for this assignment, constant time for this last assignment, and how much time do we spend for this while loop? For the best case, as Beryl has mentioned, for the best case, the while loop iterates only once, okay? In the best case scenario, the nth item that we want to insert into our sorted array is actually the largest in the sequence, which means that I will simply compare this last element with the previous element, and this last element will already be larger than it, and we will just simply finish the while loop without executing the statements inside and without repeating the while loop in further iterations. This means that in the best case scenario, the while loop will also require constant amount of time, because we simply did just two comparisons and nothing else. We didn't repeat the while loop at all. So constant time here, constant time for this assignment, constant time for the while loop, and constant time for this last assignment. This means that the rest of the code in the best case will require some constant amount of time. Let's call it C. So this equation in here describes us the best case running time of insertion sort. Tn is equal to Tn minus 1 plus C. Again, since this is defined recursively, it's not too good for us yet. We need to expand the T of n minus 1 and further so that we will get Tn in open form. What is Tn in open form if this is its recursive definition? If Tn recursively is defined as Tn is equal to Tn minus 1 plus some constant, what is Tn in open form? Is it n squared? Is it n log n? Is it n cubed? What is it? Any guesses? It will be n. Yes, exactly. So again, I could do the same operation. I could try to expand T of n minus 1. To do that, I would simply replace, in this formula, I will simply replace n with n minus 1. I will get T of n minus 1 is equal to T of n minus 2 plus this constant C plus the constant c from the previous iteration. So this part t of n minus 2 plus c is t n minus 1, and this c is the previous c. Now if I keep on repeating this, at the end I will see that this is equal to how many c's. So each time that I do an expansion, I'm adding a constant c to my sum. And how many times do I repeat that expansion? I start with n minus 1, n minus 2, n minus 3, n minus 4, and so on. So this means that I will do the expansions n times. So the whole sum will be n times the constant c. And we will see that this is actually equivalent to theta of n, since c is simply a constant. Later on we will see a formal definition of theta. So to sum up, in the worst case, we say that insertion sort will require theta n square running time, and in the best case, it will require theta of n running time. Is the discussion clear so far? Do you have any questions regarding the algorithm insertion sort and its running time analysis? Okay, so this was a quick review of last week's lecture. Now this week, this lecture, we will start with yet another algorithm that we will design again for the sorting problem. This algorithm will be called merge sort. Again, the input of the problem is the same. We have an array with n numbers. As output, we want this array A to be in sorted order, to be in increasing order, let's say. This time we will use the divide and conquer idea to design our algorithm. And later on we will see that this divide and conquer idea is actually no different from doing a design based on induction. The main idea we have written down in here in 3 steps. We divide the sequence that we are working on into 2 subsequences, A1 and A2. We assume that both of them can be sorted, are sorted. So which implies, in terms of coding, recursively call your algorithm to solve the problem for this smaller sequence A1. Call your algorithm recursively to solve the problem for this second smaller sequence A2. Now in our hands we have 2 smaller sequences, A1 and A2, but both of them are sorted. So A1 is sorted within itself, A2 is sorted within itself. What remains for us to do is how to merge those 2 sequences into a single sorted sequence A. Okay. Note that, as I said before, this is simply a generalization of, again, design by induction. Remember that the main idea in induction is that how can we build a solution to our problem consisting of size n using solutions of the problem for smaller instances. In insertion sorts, our smaller instances were, one of them was just a single element, this is the nth item, and then the other smaller instance was array with n minus 1 elements. We assumed that this array with n minus 1 elements could be sorted. Note that we didn't do any explicit coding to sort this part. All we did was, in our code, just make a recursive call to sort this part of the sequence. We can always do this because we are now working with a smaller size instance. All that remained for us was to merge these 2 sequences, one of them consisting of a single element, which is the nth item, and the other one consisting of a sorted sequence of n minus 1 items. Okay. This was the main idea in insertion sort. For merge sort, again, we split the problem into smaller pieces, but this time the division is basically balanced. Okay, so we divide the sequence of n items into 2, A1 consisting of almost n divided by 2 elements, A2 consisting of almost n divided by 2 elements. And using induction, we can assume that this sequence A1 is can be sorted. In other words, call your algorithm to solve the problem recursively to sort the sequence A1. Do the same thing for A2. Again, note that we're not writing any special code for these parts. We are simply making recursive calls. What remains for us to do is take these two sorted sequences now and merge them into a whole sorted sequence. Is the main idea clear? Is there any part where you want me to repeat in this general discussion? Okay, so if the general idea is clear, let's see the specifics, how we can apply this divide and conquer idea. Again, obviously, a design based on induction to our problem of sorting to come up with the merge sort algorithm. Again, we will have two components of our design. One of them will be the base case, which will consist of the smallest instance of our problem. And then we will have the inductive part, and this is the figure of the inductive part. Basically, make a recursive call to sort this part of the array, make a recursive call to sort this part of the array. Once you have them sorted, combine them into a whole sorted sequence. Let's see the pseudocode for doing this. This is the main pseudocode. Note that in this case, for our base, so we have slightly changed the parameters. We have slightly generalized the parameters. Later on, you will see why we need these two parameters. For the merge sort, the input is the sequence A that we want to sort. Left indicates the leftmost index of the part of the array that we want to sort, and right indicates the rightmost part, the rightmost index of the array that we want to sort. So for the initial call, if our array A consists of indices 1 to n, we will simply call merge sort with A, left being equal to 1, right being equal to n. Okay, but note that this parameterization is more general. With this parameterization, we can actually call the merge sort algorithm to sort any part of this array A. Okay, so if I want to sort in between indices and 100, I can make this call A, 10, and 100. That call wouldn't touch the rest of the array. It would simply sort the part of the array in between indices 10 and 100. Okay. Later on, we will see why we need this parameterization. Now, given this parameterization, what is the base case of our design? Note that base case corresponds to the smallest instance of the problem. In the smallest instance of the sorting problem, the part of the array that we want to sort consists simply of a single element. Or in other words, in the simplest instance, left is equal to right, which means that there's only a single element that we want to sort. If that is the case, that part of the array, which is a single element, is already sorted, which means that for the base case, we don't need to write any explicit code. Okay, so you can assume that just before this if statement, we have the following code. If left is equal to right, simply return. Since it's simply returning, we didn't write any code for that part. Now, this is the inductive component corresponding to this figure that we have in here, this figurative description of the algorithm. All we need to do is, so this is our left index, this is our right index, okay? We first compute a middle index. So middle is basically the average of this left and right. Okay, so middle is left plus right divided by 2. This is our middle index. Okay. Now, once we compute the middle index, what we will do is, using the description in this figure, sort the left part of the array recursively, which is this call. So this call says sort the array A in between the indices, this is left, in between the indices left and mid. This is the first recursive call. The second recursive call is to sort the right part of the array, which is here. So basically sort the array A from in between middle plus 1, this is right. Now we can assume that the left part of the array is sorted and the right part of the array is also sorted. All we are left remains for us to do is to merge these two sorted sequences. This we will do with a separate function just to make our description more clear. The function merge will basically take the array A, assuming that the array A is sorted in between left and mid within itself, and it is sorted in between the indices middle plus 1 all the way up to right within itself. What function merge will do, it will merge the whole sequence into one big sorted sequence. Let's see how the merge function should work. So this was the parameterization of our merge function. What we first do is, so remember that this was our array A. What we will first do is copy this left part of the array from the indices left all the way up to mid into a new array. Let's call it A1. This is where we do that. So copy the left part of the array A into a new array A1. And do the same thing for the right part of the array. This is the right part of the array. Copy the right part of the array A into a new array A2. Okay, so this for loop basically does that. It copies the right part of the array A into the new array A2. For convenience, we assign the last elements of A1 and A2 to some large value. Let's just consider infinity for now. It's just for the convenience of the description. You can later on see why this is why we do this. Okay, so now we can assume that we have the left part of the array in a new array called A1. We have the right part of the array A in a new array A2. And we can safely assume that A1 is sorted within itself, A2 is sorted within itself. What we will try to do is combine these two arrays into our output array A in sorted order. Okay. To do this, the idea is the following. Keep a pointer that will point to the current element of A1 that we are considering. Keep a pointer that will point to the element of the array A2 that we are considering. Initially, the left pointer of A1 points to the leftmost element. So that pointer is called index 1. Index 1 initially is just simply 1. Index 2 is also simply 1. It points to the leftmost element of A2. What we will do is each time we will compare the element under the pointer of the first array with the element under the pointer of the second array. Now, the smaller of these two, we know that must be smallest among all the elements of the original array A. Why? Because this element in here is the smallest of A1, the left part of the array. This element is the smallest among all the elements in A2. So the smaller of those two must be the smallest among all the array items A, and it belongs to the leftmost index in our output array A then. Okay, so we will simply compare these two. Whichever one is smaller, we will copy it here as the leftmost element of A. This is what we do inside this for loop. So we simply compare index 1 indexed element of A1, so A1 index 1 with A2 index 2, which if A1 index 1 is smaller, then AI will take A1 index 1. Once we do this, we will now forward the pointer that we have just moved. Okay, so if the element at A1 is smaller, we copy that element into output array A and forward its pointer to the next position by 1. This we do so that in the next iteration of the loop, now we will be comparing this element at index 2 with the current element of A2. Again, the smaller of those two must be the smallest in the array A among the remaining items. And again, take the smaller of those two, replace it in the output array A, and forward the pointer where we have done the moving. So if this was smaller, then again we will forward A1's pointer to the next element. And then again we will compare this item with the first item of A2, whichever one is smaller, again move it to the output and then forward the pointer. So let's say for this time it's now this one. If this one were smaller, then now we will move this one's pointer. So that in the next iteration of the for loop, we will now compare these two current elements. Okay. So this is the main idea. Is the main idea clear? The main idea of the merge sort algorithm. Once we finish this, once we finish all the iterations of this for loop, we will now have the whole array A in sorted order. Okay, so is this part especially, so merge, the algorithm merge itself is not too complicated. First part is just copy the left part of the array into A1, copy the right part of the array into A2, and now compare elements of A1 and A2 one by one, whichever is smaller, put it into output and pointer, and keep on doing this until you fill the whole array A. Can everybody see that the array A at the end must be completely in sorted order? Are we all clear about the pseudocode, about especially this merge part? This is the part where we are doing the merging of those two sorted arrays A1, A2 into a sorted sequence A. Any questions about this? Can you all still hear me, or are you all still following the lecture? Okay, any part that is not clear regarding the pseudocode? Okay, once more, let's go over this merge sort algorithm on a sample instance. So let's say that our array A initially has 8 elements indexed 1 through 8. Okay, this is our array A. How does the merge sort algorithm work? It first divides the array into two, finds the middle index. It recursively sorts the left parts, recursively sorts the right part. So this is the division point. It says merge sort this part of the array, merge sort this part of the array, which in turn will call merge sort as well, which will in its turn again divide the array into two. It will say sort this part of the array, sort this part of the array. In their turn, they do the same thing. We divide the array with two elements into two. It will say merge sort this part of the array, merge sort this part of the array. So at this level, we now have our base cases. And for the base case, we don't do anything. This is sorted within itself. This is sorted within itself. And so this part is done. This part is done, and we do the merge call. So merge call will simply take this as a sorted array, this as a sorted array, and it will combine them into a single sorted array. How does it do that? It has its pointer pointing to 6. a pointer pointing to 2 for the right array, it will compare them, take the smaller one, assign as the leftmost element of the output array, and then forward the pointer. Note why we place the infinity in here. So comparing 2 and 6, 2 is placed in the output array, and then the next pointer of the array A2 now points to actually to infinity. Okay, and in our next iteration of this for loop in here, we will compare the current element of A1, which is 6, and the current element of A2, which is infinity, and 6 will be smaller, and we will now have placed 6 into its proper position. And we will forward the pointer of the array A1, which will now point to its infinity value. But now we have the array A in sorted order. Now we will do this for every subarray in here, which will complete their merges and will return their results. And now we will call the merge algorithm for this sequence and this sequence. Again, the idea will be the same, but let's see how the merge algorithm works in this last instance. So our left pointer points, our index 1 points to 2, our index 2 points to 1. Okay, just in here, index 1 points to the leftmost element of A1, index 2 points to the leftmost element of A2. Within a loop, within this loop, we will keep on comparing the current items of A1 and A2 and place the smaller one into our output array A and forward the current pointer of the proper array, whichever one we have done the placing from. So we will compare elements 2 and 1. 1 is smaller, we will place it into our output array A, and we will forward the pointer of array A2 to the next position. Now the current item of A2 is 9, current item of A1 is 2. Again, we compare those current items, 2 versus 9. 2 is smaller, so we place 2 next into our output array, and then we forward the pointer of array A1 into the next position, so that now the current element of A1 is 5, current element of A2 is 9. Again, we do the comparison. 5 is smaller, so we place 5 into our output array next and forward the pointer of A1 to the next position, so that it will be pointing to 6. In the next iteration, compare 6 versus 9. 6 is smaller, place it in the output and forward this pointer to the next position. In the next iteration, compare 8 versus 9. 8 is smaller, place 8 as the next element in the array A and forward the pointer. So note that we have an artificial element in here, which is infinity in our left array A1. Well, the same is true for A2 as well. An artificial element infinity in here. So our current pointer now for A1 points to infinity. The current pointer for A2 points to 9. Compare them. So we place infinity artificially so that the same type of comparison that we do in this for loop will work fine if we finish the elements of one of the arrays. So in this case, the elements of the array A1 are finished, and using exactly the same comparison within the for loop, we can actually place the rest of the items of A2 into our output array. If we keep on doing the same comparison, we will compare 9 with infinity. 9 is smaller, place 9 into output array, forward this pointer, pointing to 10 now. Compare 10 versus infinity. 10 is smaller, place 10 in the output array, and forward this pointer. Finally, compare 12 with infinity. 12 is smaller, place it in the array A. Now that we have placed n items of the array, the for loop finishes, and now we have the array A in sorted order. Okay. Any questions about all this discussion? So, is the sample simulation of the merge sort algorithm also clear? Do you have any questions about how the merge sort algorithm actually executes if it's given this input sequence? Okay, let me ask the following question then. Can anybody tell us why we need this parameterization? So for instance, for the insertion sort, our parameterization was input array A and N, meaning that sort A consisting of N items. But for merge sort, we said we now extend our parameterization, saying that merge sort will mean that sort A in between indices left and right. Why not simply parameterize with N in here? Why not simply use N as our parameter, saying that sort A consisting of N items? Any guesses? Any answers? Or can you answer by looking at this figure, basically a sample run of our merge sort? So Asena has an answer because we divided into sub-arrays. Exactly. So we have the left and right indices because merge sort algorithm divides the array into two pieces. Okay, and at some point throughout our recursive calls, we will, for instance, need to say that, okay, for instance, sort this part of the array. To be able to say this, we have to tell that this is the leftmost array, this is the leftmost element of the array that we want to sort, and this is the rightmost part of the array that we want to sort. So with merge sort, unlike insertion sort, it could be the case that we need to sort different areas in the array, different areas indicated by their left and right indices. Okay, so it's basically how recursive, it's due to the fact that the recursive calls to merge sort can actually be done in between any two indices inside the array A, because that's how the design of the merge sort is done. All right, I'm hoping that this part is also clear. Any other questions? Does anybody have any questions regarding the merge sort algorithm, regarding its correctness or regarding how it works? Is all the discussion so far clear? Okay, so our next step would be, remember that we first design an algorithm, and note that the design that we have just done is also based on induction, because the main idea again is to come up with a solution to a problem using solutions of smaller subproblems. In this case, the smaller subproblems are simply left half of the array, right half of the array. We are saying that, okay, let's assume we can solve the problem for this smaller input, and let's assume that we can solve the problem for the smaller input consisting of the right half, and then how do we combine those two solutions into a bigger solution? This is again, the main idea is again based on induction. Our next step would be to do a running time analysis of this algorithm. How much running time would this algorithm require? So if we denote the running time spent by the merge sort algorithm on an array A of n items, how would we describe T of n? Okay, that would be the next thing to do, but let's do that in tomorrow's lecture. Let's not do it today because we don't have too much time left for this lecture. So if you don't have any further questions, So tomorrow we will again have lectures, almost 2 hours on Tuesday tomorrow. And in that lecture we will first start out by analyzing the running time of this merge sort algorithm, and then next we will talk about, so far we have been talking about the theta notation informally. We will formalize that discussion and formally define the asymptotic notations and the most useful ones, basically theta notation, big O, omega notation. We will see their formal definitions. So that's the stuff for tomorrow. If you don't have any further questions, we can stop our lecture for today. Does anybody have any questions? Okay then, thank you, and I'll see you tomorrow then.